Welcome to lecture 14, everybody. Lots of cool stuff to talk about today. We're going to wrap up the gradient descent material we started in the last lecture, and then we're also going to talk a little bit about feature engineering related to some of the transformations that we did in visualizations and simple linear regression. Like I said, we're going to wrap up what we did last time. We're going to be using scikit-learn a little bit more today. Today, we will wrap up gradient descent and do some feature engineering, and then you're off for the weekend. All right. So let's continue where we left off last time. I want to do a couple slides to just get you back into the mindset of gradient descent, since last time was the first time a lot of you have seen it. So let's just remember what we're trying to do when we fit a model. We're trying to identify the value of theta that minimizes some loss function, some average loss for all of our data points. We want to identify the theta value that gives us the lowest possible loss. That has been the goal to all of our model fitting so far. Last time we talked a bit about this idea of finding those optimal theta parameters. We've talked about using calculus, we've talked about using geometry, but gradient descent was this sort of multi-purpose way of doing this for lots of different types of models. We update our set of parameters, in this case, a one-dimensional parameter. We start with the current parameter, and then we follow the negative derivative. We work our way down the loss function. We work our way down the loss function to identify the parameter or set of parameters that minimizes that loss function. And we also talked about this idea of a learning rate, so we weren't taking steps that were too large. Okay, and then we did it in multiple dimensions. Towards the end, we talked about taking that expression up here and doing the exact same thing, just in multiple dimensions. Instead of just a scalar value of theta, we now have a vector of theta values that are updated in exactly the same way, except instead of following the derivative, okay, of a one-dimensional function, we're following what's called the gradient, or the negative gradient of some multidimensional function. Okay, so we're following this multidimensional loss surface. We're trying to find the very bottom of that loss surface and identify the set of parameters that minimizes that loss function. Okay, if we want to see a picture of this, it looks something like this. In this case, we have a 3D loss surface. For each combination of theta naught, you can think of like an intercept term. Each combination of theta naught and theta 1, the slope term, we have some value of loss. Our goal is to try to make it to this point, the set of theta values that minimizes our loss function. Now, how do we do that? We follow the negative gradient. We take the partial derivative with respect to the first parameter and the partial derivative with respect to the second parameter and follow the negative gradient. The negative gradient points in the downhill direction. It points in the downhill direction. We follow that gradient, that negative gradient, and we end up, hopefully, at a global minimum. Gradient descent gets us to a local minimum. If we have a convex loss function, it'll get us to a global minimum. Okay, so this was what we were talking about last time. Let's just do a quick review. We'll open up with a Slido already. Think about this one. Let's say that we have some loss function. We have some loss function with a combination of theta naught and theta 1, just like this. And it turns out when you compute the gradient, when you actually compute the value of this gradient at a particular combination of theta naught and theta 1, you get a vector -3, 2. Based on that information, which one of those is true? Give that a go. And feel free, as usual, talk with your neighbor. No need to whisper. Think about what that first term means. Think about what that second term means with respect to theta naught and theta 1 and the loss function. Wait till we get up to about 200 here. Not down. All right. So going back, how do we interpret this loss function? How do we interpret this loss function? This first element corresponds to our first parameter, theta naught. If I nudge theta naught a little bit up, This term is telling me how the loss function is going to change. So if I perturb theta naught, if I increase it by just a little bit, if I increase theta naught by just a little bit, this first element tells me what happens to loss. It's negative, so that tells me that increasing theta naught a little bit at our current choice of theta naught and theta 1 will reduce loss. Similarly, increasing theta 1 by just a tiny bit at our current set of thetas will increase loss. And so if we're trying to minimize the loss function, it looks like it's a good idea to increase theta naught and probably a good idea to decrease theta 1. Okay? So we want to understand what this gradient is telling us. It's giving us driving instructions for a local minimum. Okay, so again, this is what we just said. How does we interpret element 1? If we barely increase theta naught, how does the loss change? If we were to barely increase theta 1, how does the loss change at some point, at some set of theta naught and theta 1 values? Okay, so we have a gradient at each of those combinations. All right, so let's put it all together now. Let's put together everything in the last like 4 or 5 lectures in one slide. Okay, so let's put things together. So we learned this first. We learned how to state a model. We learned how to state some loss function on individual data points. And then we learned about this idea of average loss. So in this case, let's say we fit a model. This looks a lot like simple linear regression. In simple linear regression, x naught would just always be 1. For the purposes of this problem, let's just assume it can take on any value. So really, this is like a multiple regression model that doesn't have an intercept, but has 2 parameters. We're going to use mean squared error as our loss. Again, that's something we choose. Okay, this is squared error as loss on an individual data point. This is the mean squared error. This is something we did several lectures back. So then we learned about gradient descent. How do we actually identify the values of theta naught and theta 1 that make this loss function as small as possible? We talked about this idea of gradient descent. This is 2 ways of writing the exact same thing. We're going to update our theta by subtracting some learning rate multiplied by the gradient. Okay, we're going to follow the loss surface to where we have a local minimum, the closest local minimum. Okay, this is the gradient descent update rule. Now, how do you actually put this thing in practice? To put this thing in practice, we need to actually go compute those values. Notice to take the partial derivative of the loss function, we need to have the loss function in hand. And then when we take a partial derivative of the loss function, what ends up happening? So at the top right here, the top right expression, all we did, notice that this is the same thing as the expression before. This is the same thing as this expression if I were to take away the 2 gradient operators, the nabla, the upside down triangle. But it works just like a derivative where if I take the gradient of both sides, the 1 over n constant pops out, and the gradient of the sum is the same idea as the sum of the gradient. That's all that's saying. And so to derive the gradient of our average loss, we need to take the gradient of our individual level loss, which is defined right here. We can take y hat, plug it in for the y hat in this expression, and take partial derivatives. Now on the skipped slides, I have the derivation for the gradient of the individual data point loss. You can go check it out. It's no different than what we've done so far. Okay, standard partial derivatives. Once we've taken those partial derivatives, we end up with the gradient of the individual level loss. We can work our way backwards and perform gradient descent. We have all of the ingredients we need to run gradient descent. We start with some guess of theta. We plug in that guess. We plug in each value of xi, each value of yi. Those are constants. That gives us a gradient. We average that over all data points, and we iterate. Get a new set of thetas and keep going, okay, until convergence. All right, so that's gradient descent all in one slide. Take a look at the skip slides if you're interested in the derivation of that quantity, similar to what we've seen before. One other thing to keep in mind, these issues we had before with convexity, where when we had a nice convex function, we would always end up at a global minimum because local minimums are global minimums for a convex function. But we might have a non-convex loss surface. Same issues when you're dealing with gradient descent in multiple dimensions. You might end up in a suboptimal local minimum. So lots of different techniques for thinking through this problem. You might try lots of different initializations, run gradient descent multiple times, see which one gives you the lowest value of the loss function. Just keep in mind that this problem exists. Keep that in mind. Convexity is still an issue in multiple dimensions. Okay, so now we're doing brand new material. Brand new material, let's now take this gradient descent idea and see if we can do it more efficiently. Can we do this more efficiently using some tricks? So here's our gradient descent update rule. We saw this on the previous slides. We have some theta value, we update it by following the negative gradient. Okay, what is the gradient of the loss function? We have to do the gradient of the individual level loss. It's the average of the gradient of the individual level loss. To compute this quantity, we need to iterate through all n data points, and we need to take partial derivatives for all d parameters. We'd been using p plus 1 before. In this case, we're just saying we have d parameters for which we need to compute. And so this is running at a time complexity on the order of n times d. Now keep in mind, we have to run gradient descent over and over. It's an iterative process. So if we run this, let's say for t iterations, 10,000 iterations, the final time complexity looks something like this. And this can grow pretty large. Typically of those quantities, n, your number of data points, is by far the largest term. We could have millions or billions or trillions of data points that we're working with. And so computing this gradient just once can be really computationally expensive. And we're going to have to do it over and over to try to get an optimal value of theta. So can we do this any more efficiently? Fortunately, we had a lecture on sampling. Let's see if we can take sampling and make this whole process a little bit more efficient. Okay, instead of having to pass through all n data points for every update. So I want to give you some terminology first. This idea of an epoch and this idea of an update. Okay? What is an epoch? An epoch is when you pass through all n data points, one pass through all n of your data points in the process of updating your parameters. Okay, so regardless of the number of updates, it's just one pass through all of your data points. So getting the exact gradient like this, like we've been doing so far, requires us to compute the gradient of loss on all of our n individual data points. That's one epoch. What is an update? An update is using the gradient or some approximation of it to update the parameters. So this is one epoch of gradient descent with one update to the parameter vector. Okay, epoch, one pass through all the data points. One update, it's when you update your parameters once using the value of the gradient in your learning rate. Okay, so let's see if we can start changing these values a little bit and playing around with them. So I'll give you a picture. This is a picture of what we just saw. This is what we just saw. Let's imagine we have all n data points. All n data points. We compute the gradient for all n data points, the average loss for some combination of thetas. When we do that, that is one update to the parameters. This is what we've seen so far. And it's one epoch. We've passed through the data set one time. I want to give you a new way of thinking about this. Let's imagine we take our data set, we randomly shuffle it, and we split it in two. Okay, take essentially a simple random sample or a stratified random sample of size 2, where I just randomly set up the strata. Okay, and I now have two subsets of my data. They were randomly sampled, so presumably they are pretty representative of the entire data set. But now I have two subsamples. Okay, these are supposedly pretty representative of the original data set. So what if I approximated the gradient using each of those subsamples? So using half of the data set, we randomly split this thing in half. Instead of computing the exact gradient, the average of the loss over all n data points, what if I just computed the average of the gradient of the loss over just half of my data points? That half of my data points is representative, presumably, of the rest of the data. So this should be a pretty darn good estimate of the gradient of the loss. And I can do that twice. It seems kind of like a free lunch here, right? We can get two pretty good approximations to the gradient, which allows us to do two updates using exactly the same data set. Okay, following me so far? This is what's known as mini-batch gradient descent. Mini-batch gradient descent. We use a simple random sample to approximate the gradient. Okay, simple random sample to approximate the gradient, making sure that it's really, in a sense, a stratified sample. We're splitting our data at a random point and using all of the data points at least once. Okay, data points aren't going to be reused across batches here until we've completed an epoch. So imagine you sample B records in your data set. In the previous case, we sampled n over 2 records. And then you approximate the gradient by just taking the average of the gradient of the individual data point level loss for those B data points. And that is now your approximation of the gradient. Those were randomly sampled. Those B points were randomly sampled, so you'd hope that they are representative of your entire data set. Okay? That is called a mini batch gradient. This is a mini batch gradient. Okay, this is called a batch gradient or just the exact gradient. Now, our time complexity has gone down. Instead of n times d, to get a single gradient, we're getting an approximate gradient with b computations of the gradient of loss instead of n. So we have a smaller batch size, and then we still have d parameters. So we've now reduced our time complexity. Our estimate of the gradient is a little bit worse, but we'd hope it's still pretty representative. Okay, but we're doing it faster. And so what's this trade-off? Okay, if we have a large b versus a small b, a large b is going to give you more accurate updates. This is the exact gradient. As b goes up, you're going to look more and more like the actual gradient. But what's nice about small b is you can do this faster. You get more updates per epoch, right? You get a lot of these updates. So keep in mind, it's a trade-off of accuracy and speed. And there's a couple other nuances to your choice of b that we'll step through during the next 3 slidos. So we're going to do some slidos in just a sec, but first I'll give you a visualization. So here's gradient descent from above. We're looking at a contour plot. You can imagine the axis we don't see is loss. Imagine like a parabola coming out, a 3D sort of parabolic shape. Okay, and what do we do with gradient descent? Well, let's say our initial guess for theta naught and theta 1 is this point. We do our standard gradient descent. We compute the gradient at this point, right? We work our way down the negative gradient. We end up with a new combination of theta naught and theta 1. That's one update, another update, another update, another update, another update, using an exact gradient. Mini batch gradient descent won't necessarily follow the exact perfect path through these contours, right? The perpendicular pass through these contours is the direction of steepest descent. That's the exact gradient. When we take a representative sample, we won't necessarily get the exact gradient back. And so we're going to move in that direction over time on average in the right place, but getting there, we won't necessarily follow the most efficient path. Okay, we're approximating the gradient. All right, 3 slidos to think through this. Let's start with this one. In general, which one of these 3 things is the least computationally expensive? Which of these would require the least computing power? What do we think? And as usual, feel free to talk with your neighbor. All right, we've gotten up pretty high. So which of these is the least computationally expensive? This is what we've seen so far. One update of gradient descent, vanilla gradient descent like we've been talking about. We pass through all n data points. We get an exact gradient. We get one update. Mini batch gradient descent, how many data points do we have to pass through? Okay, so great. So one update of mini batch gradient descent is going to be less computationally expensive. Why is this the case? We are computing an approximate gradient of the loss function, an approximate gradient of the loss function with mini batch gradient descent. Instead of passing through all n data points and taking the average of the individual data point loss over all n data points, we're only doing it over the b data points in our batch, okay, which requires less computation. We don't have to pass through n data points. To get a single update, we only had to pass through b points instead of n points. B has to be smaller than n. So gradient descent requires computations for all n data points. Okay, for a single update, mini batch gradient descent, just b. Okay, that's the first piece. Let's do another one. Which of these is the least computationally expensive? One epoch of gradient descent or one epoch of mini batch gradient descent? A little trickier. What is an epoch? An epoch is a pass through all n data points. An epoch is a pass through all n data points. What does that get you for gradient descent? What does that get you for mini batch gradient descent? So one epoch of gradient descent updates is going to be the least computationally expensive. Quite a split. Quite a split here. What do we think is going on? So let's talk through this. Both of these two things require a loss computation for all n data points. That quantity will be computed n times in both of these cases. What is an epoch? It's a pass through all n data points. We need to compute the gradient of the individual data point level loss for all n data points. So we know that's going to happen in both cases. So that's the same. But what else is going on? In gradient descent, that gives us a single update to the parameters. In gradient descent, we're going to get a single update. We're going to use all n data points to compute the gradient. Okay? We're going to get one update from that gradient. What do we get in mini batch? In mini batch, we're going to get a bunch of estimates of the gradient. We're going to get n over b updates to the parameters. So let's say I did batches of size 10. I'm going to have to update my parameters n over 10 times, however many times I can fit 10 into all of my data points. Those parameter updates also take up computation. So there are a lot more parameter updates in mini batch gradient descent. So one epoch of mini batch gradient descent requires more updates. That's why one epoch of gradient descent is more computationally efficient. A little funky. And now keep in mind, there's some other benefits you can think about. So when we compute things serially, we have to compute them one after the other. When we compute things in parallel, we can send them to multiple nodes at the same time and get all of our computations faster than if we did them one after the other. So within a single update, so using just a single update, one of these, the loss on individual data points, or the gradient, excuse me, of the loss on individual data points, I should update that. The gradient of the loss on individual data points, the gradient of the loss on individual data points, can be computed in parallel. Why is that? We're just going to take an average. These loss computations, these gradient of the loss computations here, they don't depend on one another. I can compute those for all n data points in parallel. And so I can speed things up within an update. Within a single update, I can do that. The problem is updates themselves cannot be computed in parallel because each update depends on the previous update. To get theta t plus 1, I need theta t. So I cannot parallelize the process of updating my parameters. And so gradient descent, vanilla gradient descent, can benefit more from the parallelism that we get from these loss computations done in parallel. But batch gradient descent, mini batch gradient descent, excuse me, cannot benefit from this because we have to do our updates serially, one after the other. Okay, so this is another thing to keep in mind with gradient descent versus mini batch gradient descent. So then the question is, which one should we use? Right, like, is mini batch gradient descent, like, this is neat, this is cool, we can do things faster, but does it get us any benefit? Is it any more efficient? So let me ask you, which one of these two approaches will get you closer to a minimum of a function, given the same number of iterations, let's say, given the same number of updates? Which one of these is going to get you closer to the minimum of a function? One epoch of gradient descent, we're going to get a exact gradient. It's going to be a perfect gradient. One epoch of mini batch gradient descent, we're going to get a bunch of approximate gradients, but we're going to get then multiple updates. Which one is better? Which one is better? So let me give you some visual intuition for the answer here. So again, we're pretty split. Again, we're pretty split. Super interesting. So some really nice visual intuition is coming. Turns out that one epoch of mini-batch gradient descent gets you closer. It is more efficient. So here's a picture. So what we're looking at on the left here is one epoch of vanilla gradient descent. Okay, of standard gradient descent, what we've been learning so far, we get a perfect estimate of the gradient, right? We're getting the exact gradient, and we can follow that exact gradient, and we get one update. So we start at this set of parameters. In this case, we have B and W here, and with our perfect update, with a perfect gradient, we end up here. So that's one update and one epoch. What do we get with mini-batch gradient descent in one epoch? So in one epoch, we get many updates, many approximate updates, right? They're approximations of the gradient. And so we don't end up climbing this gradient in the most optimal direction. Notice this first update doesn't really get us very far. This one gets us way too far. It overshoots. These get us a little bit closer. But notice after one epoch, I am closer to the true minimum of the function using mini-batch gradient descent. So it more efficiently gets you there. Okay, these approximations are pretty darn good. It's a little bit like a drunken man walking down a hill, sort of aiming for the right spot. Okay, so this is good to know. Mini-batch gradient descent is more efficient per pass through your data points, per epoch. So let's now take this to an extreme. I want to take this to the extreme. What is the smallest possible batch? What is the smallest possible batch size? We'd worked with a batch size of n over 2. What if we kept chopping our data set up and got the smallest possible batch? We couldn't cut data points in half, but what if we randomly shuffle our data set and we split it into n pieces, effectively just extracting each individual data point? Little weird. I'm going to approximate the loss on all of my data points, the gradient of the loss on all of my data points, with the gradient of a single data point. Just one. Just a single gradient, a batch size of 1. This seems very weird. And I'm going to do this over and over. So I'm going to end up getting n of these approximate gradients. And these are really going to be, weak approximations, right? On average, as long as you're randomly sampling, you're getting a representative sample, but that's in the long run. These individual gradient updates are going to be very different than the true gradient. But as it turns out, this actually does pretty well. This is called stochastic gradient descent. We sample just a single record. We use that single record to estimate the gradient. We compute the individual data point gradient. We use that as our estimate of the gradient of the average loss. The computation here, we have a single gradient computation for d parameters. So we've taken our time complexity down from n times d. Remember, n is super, super large. That can be millions, billions, trillions of observations. We've taken it down to on the order of d. Okay, much faster. This is called stochastic gradient descent, something you should be aware of. So stochastic gradient descent is a subset of mini-batch gradient descent. It's simply mini-batch gradient descent with a sample size of 1, or batch size, excuse me, of 1. Okay, this is called stochastic gradient descent. And depending on the problem you're working on, again, SGD might make the most sense. You might want to do mini-batch gradient descent with just a couple points in each batch. Depends on the nature of the problem, but you want to be familiar with these terms. Okay, that takes us almost to the end of gradient descent. Why don't we do one more Slido here? Let's do one more Slido just to make sure you understand stochastic gradient descent, and then we'll move on to feature engineering. A little bit different here. What is stochastic gradient descent related to mini-batch gradient descent? So one epoch is one pass through all of the data points. One pass through all of the data points. In stochastic gradient descent, we estimate the gradient, we approximate the gradient using the gradient computations on individual data points. Each data point is going to give you its own approximation of the gradient, and then you're going to get their own update. So with 8,192 data points in stochastic gradient descent, you're going to get 8,192 updates to your parameters. Okay, that's SGD, stochastic gradient descent, used to fit lots of different models. Variants of SGD are used to fit lots of different models out there. Okay, that takes us to the end of gradient descent. You now know gradient descent. All right, so now we're going to shift gears to something almost totally new, feature engineering. So before we were talking about how to fit a model, how to find the optimal set of parameters, how do we now modify our features to get a better model? What exactly is feature engineering? So we've actually seen feature engineering before. This isn't a new thing. We've seen this before. We've seen that nonlinear data, so this was that dugong relationship, the relationship between the length of a dugong and the age of a dugong. We saw that this was a nonlinear relationship. And if we fit a simple linear regression to this data, we got a residual plot that looked like it wasn't randomly scattered. We can see already here, it's not a great fit. This really should be a curved line. But using our knowledge of transformations from visualization, this age at large values of length looks pretty unconstrained. So if we take the logarithm of age, this ends up linearizing our data set. And if we fit a simple linear regression where our outcome is log age instead of age, remember, simple linear regression doesn't know about log age versus age. It's just looking at a column of numbers. We end up with a much tighter fit. And if we were to transform this back to age, we would end up with a curved line. Okay, so we've seen this before. We've seen this idea of transforming parts of our model. What is feature engineering? Feature engineering is the idea of taking your raw features and making them more informative. We can use lots of outside knowledge to make them more informative. We can do transformations like we just saw before. So for example, if I were to take a feature, before we saw it with an outcome, a feature X, and I were to take the logarithm of that feature, that's feature engineering. If I were to take some qualitative feature like grade level, 9th, 10th, 11th, 12th grade, keep in mind that linear regression doesn't know what a string is. It can only use numeric inputs. How do I take 9, 10, 11, and 12 and put it inside of linear regression? I could actually use 9, 10, 11, and 12, but that numeric representation might not be very useful. Right? That might not be very useful to me. I might want to have categories for each of those grade levels. That's feature engineering. Let's say you have a data set where you have latitude and longitude. Okay, latitude and longitude for a bunch of different homes. And you want to know what's the distance to the nearest school. You can join in another data set that has schools and their lat long, and you can turn that lat long, which isn't very useful on its own in your home data set, into something like the distance to the nearest school. Okay, so this process of feature engineering is critical. Really good feature engineering is what often leads to really good models, not necessarily a fancier model. You can do a lot of damage with a simple model, with just like ordinary least squares and really, really good feature engineering. This makes you very, very powerful. Okay, this makes you very, very powerful to get good at this. All right, so some notation. There's something called a feature function. What is a feature function? A feature function is a function that takes a design matrix as its input and then spits out a new design matrix that has some transformation of the features, some engineered features. So for example, what does this feature function do? This feature function, denoted by the Greek letter phi for feature, easy, right? Feature function, what does it do? It adds another column to our data set where it squares all of the values of horsepower. It could have taken away the original horsepower column. It doesn't necessarily have to grow in size, but you just want to be comfortable with this idea of taking some existing design matrix, applying some feature function to it, and then getting back a matrix that maybe has a different dimension than what you started with. Same number of rows, same number of observations, but maybe a different number of columns. That's a feature function. When you're writing a regression specification like we've been doing so far, if you're transforming your features, sometimes you'll see the x's written as lowercase phi's. Notice there's a diagonal through those phi's, not a vertical line. That's capital phi. That's another way of denoting a feature function. So this is y hat equals x theta. We've seen this before, the matrix representation for the predictions of ordinary least squares. In this case, same idea, but we've now replaced x with a capital phi to denote some design matrix that's been transformed. Okay, so you just want to be familiar with this notation of a feature function. Something to just keep in mind. Now let's actually talk about ways to do feature engineering. One-hot encoding, super, 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 super important topic. This one's really good to understand well. Almost every qualitative feature you ever deal with, you will handle with one-hot encoding. So this is an incredibly important topic. How do we do it? So data set we've seen before, tips. We have a bunch of different dining experiences. Each row is some dining experience. We know what the total bill was. We know the total bill. We know how much the waiter was tipped. We know sex. We know whether or not the people dining there were smokers. And then we know the day that this dining experience took place. Okay, Sun for Sunday. In this case, this data set only has Thursday, Friday, Saturday, and Sunday. Now before, what you have so far, your knowledge of this class so far, you would only be able to fit a simple linear regression with those two columns. If there were more numeric columns, you could fit OLS. Using just this data set, it looks like the only two numeric columns are total bill, that's an input, and tip, that's the outcome here. How do we use all of this information? It would be nice if we could take advantage of this information. Presumably people maybe get larger tips on Fridays versus Saturdays, let's say. Maybe they're lower on Thursdays. How do we get that information into our ordinary least squares model? That's one-hot encoding. So this is how we do it. So imagine you have a data set similar to what we had before. Similar to what we had before. So this is some column in my original data. Some column in my original data. Each of these represents an observation. So this first dining experience took place on a Sunday. This fifth one took place on a Saturday. How do I take that data and represent it numerically? How can I turn this data into a language that regression can understand? So here's what you can do. You take each unique value of that column. We're going to assume that the only unique values are Sunday, Thursday, Friday, and Saturday. Okay, and notice they're in the order that they appeared in the data set. Okay, that could happen depending on the package you're using. It might do something else. It might do alphabetical order. All we need to know is that we now have 4 new columns that each have the value of each unique value in the original data set. How do I represent Sunday with this first row? How could I represent Sunday? Well, I know it's Sunday, and I know it's not Thursday, I know it's not Friday, and I know it's not Saturday. That's a yes/no question, right? Let's do binary variables. I put a 1 in the Sunday column, 0s in the rest. So when I see a row that looks like this, it implies that it's Sunday. Same idea for the rest of the columns. When it's Thursday, we're going to put a 1 in the Thursday column. We have a 0 in all other columns. We don't ever have more than a single 1. It cannot be both Sunday and Saturday at the same time, right? In this dimension, it cannot be both Saturday and Sunday at the exact same time. It has to be one or the other, right? So these columns will always sum up to 1. There's always going to be a single value in each of these columns. That's one-hot encoding. Okay, that's one-hot encoding. And we're going to do it in Python after our break, just a moment here. So here's our new data set. Before we had a data set that looked like this. We had total bill and tip. And you might imagine we're just going to use day to start out here. We've taken that day column. We've performed one-hot encoding. And we now have a data set that looks something like this. There's also another column here, size. This is the number of people that are dining. And we're going to treat it like a numeric variable for now. But notice, in this first row, you can think, well, what day is it? Because day Sunday has a value 1, this first dining experience took place on a Sunday. This one was also on Sunday. It looks like all of these are on Sunday. Now, you might be wondering, where's the bias column? Where's the column of all ones that we learned was so important for fitting a model? We're going to see in a couple slides. For now, leave belief suspended a little bit. Those are our raw features. We didn't touch these. Total bill and size were not touched. Tip is our outcome. This is our design matrix we're looking at right now. Our outcome is stored in a separate vector. But now we have all of these one-hot encoded features. We've performed feature engineering. What does our model look like? We follow exactly the same steps that we've used before. We have a parameter for each feature. There's a parameter for each feature. Each feature is inputted, the value of that feature. And we have a regression model, just like all of the other regression models we've seen so far. Exactly the same idea. So let's play with this a little bit. How do you make a prediction? Here's your model. For each feature, we have the coefficient. These are the theta values corresponding to each of these columns. For a party of size 3 and a total bill of $50, what does the model predict? Give this one a go. Okay, so what's going on here? The coefficient for the total bill is 0.09. That means theta 1 is 0.09. Notice we fit this model without an intercept. There's no intercept term here. What was the total bill? The total bill was 50 bucks. We take our coefficient, 0.09, we multiply by 50. So all of these are correct here. Second piece, same idea. There's 3 people in the party. We multiply 3 by 0.19. And then the last question is Friday. How do we deal with these? How do we deal with these? What does it mean for it to be Friday according to the model? The model has these one-hot encoded columns to work with. We communicate the fact that it's Friday to the model by setting the day Friday column to 1. Day Friday. Why do these suddenly look a little different? Why don't these just say Fri, Sat, Sun, Thursday? We'll see why in a second. But we're going to set the Friday column to 1 and multiply by its coefficient, 0.75. All these other days must be 0. If it is Friday, we know that it cannot be any of the other days. Okay, so that's how we generate predictions with these models. Hopefully straightforward, pretty similar to how we've done OLS so far. The trickier piece with this model is interpretation. Interpretation is the kicker here. So if I actually want to take this model and interpret what's going on, well, for total bill and size, we've learned this. For every increase of 1 unit in total bill, for every increase of 1 unit in size, we expect a 0.09 increase in tip, right? 0.19 increase in tip. We've seen this before. But how do we interpret these other coefficients? So I like to think about interpreting categorical coefficients, or anytime I need to interpret a new coefficient, I like to isolate it. I like to isolate it. So what's my coefficient of interest here? This is the answer, but how do we get there? So my coefficient of interest here is theta 3. I'm trying to interpret theta 3. So how can I get theta 3 by itself? How could I get theta 3 by itself? Well, I might want to get rid of all of this. How could I get rid of that entire expression? Well, let's say I have a meal where the total bill is $0. Let's say I have a dining party with 0 people in it. That doesn't seem very realistic. Again, linear regression isn't aware of reality. Interpretations won't always make sense realistically. That's why we're the data scientists. We need to use these models to do our bidding, right? We need to interpret them the way we want to interpret them. But to the model, we could have a bill of 0 and a size of 0. Okay, we want to keep this coefficient. How could I keep this coefficient? Well, I would want to make day Friday 1. I wanted it to be Friday. And if it's Friday, it cannot be Saturday, Sunday, or Thursday. And so now, if I have a $0 bill with nobody in my party, and it's Friday, my prediction is theta 3. My prediction is theta 3. What is theta 3 specifically? Hat here, theta 3 hat is 0.75. So for a $0 bill with no customers, I would predict a tip of 75 cents. That doesn't seem very useful. Doesn't seem very useful for interpretation. So we're going to talk about a way to improve this interpretation. Can we structure the model in a different way where we get more interpretable coefficients, but we don't change our predictions? So let's go back and think about the bias column a little bit here. So keep in mind, all of your one-hot encoded columns are going to sum to 1. If I added up all of those rows, I end up with a column of 1s. If I include all of these in my design matrix, what's going to happen? If I include all of these columns in my design matrix, what happens? These columns are linearly dependent. Using these 4 columns, if I add all these columns, a linear combination of these 4 columns will give me the bias column. If we have linearly dependent columns in the design matrix, XTX inverse won't invert. We can't compute our OLS estimate. We have a problem. So how do we fix it? It seemed like the model fit before when we didn't include a bias column. Okay, but then we ended up in this weird world where our interpretations weren't that great. So what do we do? So we have a couple options. Option 1, this is the new thing. Omit, we're going to completely remove one of the one-hot encoded columns. We're going to call it the reference level, and we're going to get rid of it. And we will have a bias column. I'll explain what happens with this in a minute. We could exclude the bias column entirely. This is what we did before. but we end up with sort of funky interpretations. Another thing we can do is what's called regularization. We're going to learn this in a few lectures. This linear dependence problem isn't as big of a deal when it comes to regularization, but that's coming in a little bit. So, like I said, we could either omit one of the one-hot encoded columns. If I were to completely delete this Friday column, these columns are no longer linearly dependent. You can look at this row. There's no way for me to add up 3 zeros and multiply by some number to get 1. So I could omit the Friday column and call it my reference level. What do I mean by that? We're getting there in a second. Or I could get rid of my bias column, something I've already been doing. Keep in mind, in both of these cases, the same information is being computed. The exact same information is being computed in both of these cases. Okay? In both of these cases, the omitted column is a linear combination of the remaining columns. We have the same information in both cases. So that's why the models that we fit are going to generate exactly the same predictions. But we're going to get some convenient interpretations by using the left-hand side. So let's do that now. So if I fit a model without Friday, so I'm going to fit a model using the specification on the left, I end up with a model that looks like this. Okay, very, very similar to what we had before. We no longer told the regression algorithm about the Friday column. So notice there's no longer a coefficient corresponding to the Friday column. But we did give it a bias column, so we now have an intercept. What is the intercept? The intercept 0.75. What was 0.75 before? Day Friday. That's not an accident. Okay, let's go further. Go back here. So how do we interpret 0.75? Well, let's do our interpretations exactly the same way as before. Get rid of everything else. How can I isolate this intercept term? Well, let's say I have a bill that's $0. I have a group that's of size 0, and it's not Saturday, Sunday, or Thursday. If it's not Saturday, Sunday, or Thursday, what day is it? According to this data set, it must be Friday. So for a $0 bill with no people on a Friday, that's my intercept. That's my prediction. What is the predicted tip on the reference level day? Your intercept now represents predictions when your categorical variables are at their reference levels. You might be saying, well, this is exactly the same interpretation as before. Like, why is this any better? The real benefit comes in these other coefficients. How do we now interpret these other coefficients? So what about this Saturday coefficient? How could I get this Saturday coefficient to show up? Well, what if I did exactly the same thing as before? I had a 0 bill, I had 0 size. I'll have the intercept, but I will make it Saturday. I will now give day Saturday a value of 1. I will now give day Saturday a value of 1. In that case, my prediction is theta naught plus theta 3. So theta naught is the predicted tip on a Friday for a bill of size 0, or a bill of $0 and no size, no people there. What is theta 3? It's the change in the size of the bill. So I expect, relative to Friday, that tips on Saturday for the same size bill in the same number of people will be 12 cents lower. Does that follow expectations? Yeah, Friday nights are pretty popular. Maybe Saturday people don't give as large of tips. Okay, so we get this nice interpretation. You can recover that negative 0.12 from the old coefficient table. I think the Saturday coefficient in the other table was about 0.12, 0.13 smaller than this. It's all due to rounding. Okay, again, these are all going to give the same predictions, but just keep in mind we now have a much easier time interpreting these coefficients. How different is my tip on Saturday relative to Friday for the same size bill and the same number of people? Okay, so we get this interpretability benefit by omitting a reference level column. We don't get any prediction benefit. Make sense? So if your model, if you don't care about interpretability and you just want to make your model predict as well as possible, you don't have to worry about this. But this is why, in general, I've been saying this, in general, it's good to include an intercept. You get this nice interpretability benefit. Okay? All right, let's just do a 2-minute break, and then we will wrap up with a demo and a little bit on polynomial terms. Feel free to come up with questions if you have them, or raise your hand, I can come to you. Let's do a demo. One hot encoding. There's more to the demo than just one hot encoding, but that's all I'm going to cover in the live lecture today. So let's go do some one hot encoding in Python. All right. So as usual, import some stuff. Okay, pandas, NumPy. The thing that's really going to help us is scikit-learn. Okay, scikit-learn is the thing that's going to allow us to do this one hot encoding today. So we're going to use that same tips data set that I've been talking about in the lecture so far. So this is built into Seaborn. Built into Seaborn, we're going to go take a look. What does this data set look like? Same as what I showed you in the lecture. Okay, we have the size column in this new time column. No big deal, nothing different here. Okay, how do we actually one hot encode now? So let's go one hot encode this day column. Let's do exactly what we just did in the slides, but now in Python. Here's just a diagram of what we did, just doesn't include Friday. But our goal here is to turn a column of Sunday, Thursday, Friday, and Saturday into a set of columns with Sunday, Thursday, Saturday, and Friday. Okay, so what do we need to do? Well, if we're going to fit a model predicting tips from the bill, the number of people, and the day, let's go create a design matrix that only includes the total bill, the size, and the day. And then Y is just our outcome. So we're going to use these now to fit a multiple regression model. Okay, so how do we do it? It's very similar to what we did before, where we state what model we want, right? We fit that model to some data, and then using that fitted model, we can generate predictions. Very similar idea with this thing called one hot encoder. This is a class of sklearn that does one hot encoding. You state that you want a one hot encode. You fit that one hot encoder to the columns you want a one hot encode, and then you use this dot transform method to get back your one hot encodings. So it's very similar to predicting. Okay, you're like predicting within the features, but you're not really predicting. You're getting like an exact representation of what you started with. So let's do this. The first two steps are kind of the fastest and the most straightforward, I think. So we're going to import from this sklearn pre-processing module this class called one hot encoder. We are going to initialize a one hot encoder object. I'm calling it OHE, one hot encoder. And I'm going to fit that one hot encoder object to the day column of the tips data frame. Okay, so just like before, I get something that looks like this in JupyterLab. In the background, it has been fitted. Let's go prove that it's actually working as intended. So again, first two steps are pretty straightforward. Let's go play around with this object a little bit more. So first of all, I just want to show you that this one hot encoder recognizes what values are in the data set. Okay, let me do this too. I'm going to clear outputs so that I can see. Oh, maybe I'll just show you what they are. Okay, so if I run one hot encoder.get feature names out, I use this method. What does it give me back? It gives me an array that names all of the different values that it saw in the column of interest. So in this day column, it saw the values Friday, Saturday, Sunday, and Thursday. Okay, and then notice what else it's doing. It doesn't use the values Friday, Saturday, Sunday, and Thursday as labels. It does something where it takes the name of the column, so the day column, it uses an underscore and then puts the actual value. This is very common in other languages too. You can change this default if you want, but this is a pretty common default. Okay, and so just to show you that this one hot encoder actually works, let's run it. I'm going to run one hot encode.transform, and I'm going to run it on a dummy data set containing 3 observations. It's a list of lists. The first observation is a Saturday. The second one is also a Saturday. The third one is a Friday. Presumably, when I run this, I'm going to get back some of these 0, 1 rows that we've been talking about. But what I get back is something called a sparse matrix. This is a special data type that more efficiently stores matrices that have a lot of zeros, what are called sparse matrices. We don't need to worry about that right now. We're working with pretty small data sets. We don't want a sparse matrix. We want what's called a dense matrix, or sort of the standard representation of a matrix. So we're going to convert that sparse matrix that we get back into a matrix using this toArray method. And we do that, and we get what we expect now. We get what we expect. Notice in the first row, we have a 1 here, a 1 here, and the last row, we have the 1 out in front. Why are they placed in those positions? Notice day Friday is the first element, it's the first feature. that the one-hot encoder saw. Notice the last element corresponds to a Friday as well. Saturday is the second element. Okay, that's why the ones here are second, and so on. Okay, that's a one-hot encoder. Now notice, if I try to use this one-hot encoder on a value that it hasn't seen before, like fun day, or even Monday, or pick any day other than the 4 we're working with, we get an error. The one-hot encoder has never seen anything like fun day before. It doesn't know how to handle it. And this might seem like a toy example, but you might imagine fitting some data set, fitting some model to some data set that you have, and then applying it to a new data set, and that new data set might have categories you've never seen before. This happens all the time. And so you have to handle that on the back end. You have to think about how is your one-hot encoder going to handle categories it's never seen before. Okay, that's a problem sort of out of the scope of this lecture, but just keep in mind this isn't some toy example here. This happens all the time. Happens all the time. Okay, so just keep in mind you should only be using your one-hot encoder in cases where it's going to see the values that it has already seen in its training data. Okay, we keep going down here. Down, down, down. What can we do? So let's now actually go encode the full column. So we're taking the full column of days from the tips data frame, we're transforming it with our one-hot encoder, and then converting it to what's called a dense matrix, the standard representation of a matrix. Let's see what it looks like. We run it. Remember all of those rows in the lecture, they were all Sunday. They were all Sunday. Notice in this case, same idea. Everything is the Sunday representation. 0 for Friday, 0 for Saturday, 1 for Sunday, 0 for Thursday. Okay, so we've now one-hot encoded our columns, and we now have a matrix. But we like working with data frames, so let's now go put this inside of a data frame. We're going to go convert it to a data frame. So how do we convert this into a data frame? We use our function that we're very familiar with, pd.dataframe. We're just going to dump that matrix right inside. And we want to name the columns using that getFeatureNamesOut function we saw before. This is going to give us those feature names we saw before, day Friday, day Saturday, day Sunday, day Thursday. We run this, and we get something that looks a lot like a regular old data set, but now in a one-hot encoded form. This isn't my entire design matrix. This is just the piece of my design matrix that's one-hot encoded. Okay, I have other columns in my design matrix that I want to take into account when I do predictions. So I need to go take this matrix and go join it in to the rest of my design matrix. So let's do that. Let's go do that. So we just join it over. It's in exactly the same order. It's in exactly the same order. We're one-hot encoding. We're not changing any ordering. Okay, so we join it right over. And now we have a design matrix that we want. Notice also we're dropping the original day column. We're dropping the original day column that has Sunday, Friday, and so on, because linear regression can't read strings. So we've dropped that column. We now have a design matrix that's all numeric. Now we can run linear regression. Let's do that. So we're going to use the same linear regression function we've seen before. So we're importing this from the linear model module. We're importing this linear regression class. We do the same steps we saw before. We initialize the model. We say, I want to fit linear regression. We then fit it to some data set, and then we can generate predictions all we want. So let's do that. We are going to first state that we want to fit a linear regression model. Notice we tell it, don't fit with an intercept. Don't fit with an intercept. We saw the reasons why in lecture this would give us problems. We'd end up with linear dependence. If we use the X, the design matrix right here, we do not want to add a column of ones. Otherwise, we're going to have linear dependence. So what we do is we explicitly have to tell sklearn, don't include an intercept, don't fit an intercept. By default, sklearn will fit an intercept. sklearn knows that it's generally a good idea to include an intercept. We're not going to do it right here. We're going to repeat it again with an intercept in a moment. We fit our model to the design matrix, take a look at our coefficients. We get exactly what we saw in the lecture. Okay, we get a coefficient for Friday, Saturday, Sunday, and Thursday. There's no intercept, and we get those interpretations that aren't the most useful. However, this will give us predictions that are exactly the same as the model with more useful interpretations. Let's now go build the model with the more useful interpretations. And just to note, if you try to extract the intercept from this model, it doesn't give you an error. It says that the intercept is 0. Setting an intercept to be 0 means it won't affect your model. If theta naught is 0, it doesn't affect your prediction. So 0 is the default value of that intercept. Okay, so now what we're going to do is we're going to fit that model once again, except now I'm going to tell linear regression, include an intercept, fit an intercept. And then just keep in mind, this is the default option. So if I just ran that line of code without explicitly saying that I wanted an intercept, the default option is to fit an intercept. So this is just to be verbose. So you know that we're including an intercept, but just know that sklearn by default for linear regression will include an intercept. Now, what do I have to do if I want to include an intercept? I need to get rid of one of my one-hot encoded columns. We chose Friday as our reference level during the lecture. We could choose any reference level we want. Okay, often it's the first thing alphabetically. As it turns out, Friday is the first alphabetically of those 4 days. But alphabetically first isn't always great. Back in the day, I did a project where we were looking at college admissions rates across different states. Okay, what's the first state alphabetically? Alabama. Comparing everything to Alabama might not be the best comparison point. People don't necessarily know what college admissions rates are like in Alabama. So which state do you choose? We ended up going with California. Large state, a lot of people applying to college. It's a better reference level. So just keep in mind, you don't always want to stick with the default reference level. You want to think about interpretability if that's something your data science project requires. Okay, so we drop the day Friday column, we display our matrix, and you may be asking me, where's the bias column? Where is this bias column that we so desperately need to fit an intercept? sklearn will add that bias column for us. Because we told it to fit an intercept, because that's the default option, it will handle adding a bias column and fitting an intercept for us. But we need to make sure to drop one of the levels of our one-hot encoded design matrix. Okay? All right, so let's fit it, and let's see what the coefficients look like. And hopefully you trust me, we end with an intercept coefficient, same as what we saw in the lecture, same as the day Friday coefficient from the model without an intercept. And now we get this really nice interpretability for these other coefficients. There's some other code below this that shows you how to remove the day Friday column earlier on in the process. Probably a better place to do it. It's probably a good idea when you one-hot encode your columns to state which column to drop. So notice this one-hot encoder function. You can state, go ahead and drop the first reference level, or rather first value you see. In this case, it would be Friday, right? Or the first thing alphabetically. So just keep in mind, you want to probably do this earlier on in the process as opposed to later like we just did when you create those one-hot encoded columns. Okay, that's all we're going to do for demo. Let's go ahead and go back to the lecture now. Let's go back to the lecture, and we're going to wrap up here. So let's talk polynomial features. So we've seen before that if we have curved data, we can fit a linear model to it, but it's not great, right? The residual plot doesn't look all that good. We know that we can fit a curved line to this. We've used several different transformations. We did a squaring transformation. We did a log transformation. So how do we handle this? Well, we can incorporate a non-linear feature. I told you a couple lectures ago that in simple linear regression, in the formulation we saw before, if you remember, we fit that model. We fit a model that didn't have that base horsepower term. It only had the horsepower squared term. And I said, sit tight until we get to a lecture where we learn how to properly fit quadratics. Welcome to that lecture. Okay, so we include both the baseline term and, oh, that's not what I want, the squared term. Why do we do this? Think about a parabola. I can fit more parabolas. I can fit a lot more shapes if I use that form of a parabola than if I use this form of a parabola. I can reach a lot more places with that parabola. It's more flexible. This is why this is better than just including a squared term. You'll see this most of the time in real life modeling. You include the base term along with any higher order terms that you want. Okay, so we fit this model. It's still linear in theta. This is a legit linear regression model. It is still linear in theta. The linear model does not know that this is horsepower squared. That's just a column of numbers to the regression algorithm. That's just a column of numbers to the regression algorithm. We, as the smart data scientists, know that that's horsepower squared, and we can take advantage of that. So what can we do? Well, we can fit that model, and then we can go back, realize that everything can be written just as a function of horsepower, and we actually get this nice clean curve. Remember before it only curved just a little bit. Now we're able to get this nice clean curve. If you go back to the example with dugongs and length and age, you'll get a nice clean curve when you include both the baseline term and the squared term. And notice our mean squared error went down substantially. Our mean squared error went down substantially. Before it was 24, now it's 19. That seems good. We're fitting points closer to our data set. So let's keep going. Let's add a cube term. And we get a lower mean squared error. It's not quite as big of a drop, but it is a drop. So we are fitting more closely to the points. Let's do it again. We'll add a quartic term. We get it lower again, not by that much, but it's still lower. Okay, so it seems like we can take our mean squared error further and further down with more polynomial terms. So why not keep going? Why not just fit these points as closely as possible? As it turns out, you can make a polynomial that touches every single one of these data points and has a mean squared error of 0. You can arbitrarily send your in-sample mean squared error to 0. In this case, we've only gone up to a degree 5, but we can see it still goes down. Okay, I'm going to skip the Slido and then go to here. We'll come back to that Slido. I just want to show you, because it's on my train of thought, for a set of n data points, a polynomial of degree n minus 1 can always be found that touches all of those data points. So if you have a data set with 100 data points, you can have a 99th degree polynomial and send your mean squared error all the way to 0. So why not do that? Why not do that? Given time, yeah, let's go ahead and do quick Slido here. So which one of these models do you think is the best? I'm not going to define best for you. Which one of these models do you think fits this data set the best? Based on what you know so far in the class, based on your own personal opinion, which of these models fits best? You see our constant model coming back to haunt us here. Constant model. We have the mean squared error for all these other models. Using only the information on this slide, you can actually compute the R squared of any of these models. You can actually get the R squared using just this information. Okay, so it looks like mean squared error just keeps going down. And so based on what we've learned so far in the class, we want to have a mean squared error that's as low as possible. And so based on what we know, we would want this order 5 polynomial to be the best fitting model. But there's going to be a problem with this model. There is a problem with this model, and that's what we're going to get to in these last couple minutes here. So what's the problem? Like I said, as we increase the degree of the polynomial fit to our model, we can send the mean squared error all the way to 0. We can send the mean squared error all the way to 0 if we keep adding polynomial terms, all the way up to n minus 1 polynomial terms. At that point, you're going to run into the issue where your number of features is more than your number of rows. You won't be able to invert x to x, right? But we can keep adding terms until our mean squared error is 0. And so why don't we just do that? Why don't we just keep increasing our model complexity until our error is 0? What's the problem with this? What is wrong with doing this? Have we like won the game here? So we already saw this. So let's say I have 6 data points. Let's say I have 6 data points. This is my training data set. And let's say I fit a 5th degree polynomial to these points, and it touches them all perfectly. It touches all of these points perfectly. I have a mean squared error of 0. Okay? Here's my training data. I only have 6 data points to train on. I now have to go put this model into production. That is, I have to now go use this model to make predictions in the real world. Even if those 5 data points are a random sample of the population that's out there, it's going to do a pretty horrendous job. It's going to do a pretty horrendous job of predicting on that data set. That data set is only quadratic. The data set might have looked crazy like we had. There's no guarantees that it doesn't look like that. But in general, too high degree of a polynomial will totally overfit your data. So it does really well in sample, but really poorly out of sample. You can fit your data as closely as you want in sample, but if it doesn't do well out of sample, probably not in a good position. So then what do we do? Okay, so some words here to know. We call this overfitting, when our model does not generalize well to out of sample data. So our general goal now is to try to obtain models, to try to fit models that not only fit our data closely enough, but also do well on external data sets. Okay, otherwise we do what's called overfitting. We also don't want our models to be too simple. This doesn't mean we should just fit a constant model to everything. There's a balance. There's a balance here, right? All right, so another term to be familiar with that we're going to see more later in the class called variance. You may have seen variance in the context of just like standard deviation. We've seen it earlier in this class when we computed slopes for SLR. But super complex models tend to have high variance. This is what's known as model variance. There's model bias, model variance. Right now, we're just going to talk about model variance. We'll get to the other term in a little bit later in the course. But keep in mind, if I resample data from exactly the same population, okay, all of these resamples, let's say, came from exactly the same population. If I fit a super high degree polynomial, notice that the shape of my resulting model is quite different in each case. The model is very sensitive to the choice of inputs. If I fit a constant model in all of these cases, notice that a constant model would look about the same in all three of these cases. The constant model has very low variance. It's not very sensitive to inputs, or at least it's a lot less sensitive than the polynomial model. Okay, but the constant model has its own problems, right? It's not doing a very good job of predicting. It's not leveraging the information in the data set. So low variance doesn't necessarily mean that the model is suddenly fixed. It's this trade-off. It's called the bias variance trade-off. We're going to see it later in the class. I think we're running up on the last slide here. And so this is the diagram you kind of want to go home with for overfitting. So what are we looking at here? So this is a general summary of what we've seen so far. On the x-axis, we have the model complexity, which for the purposes of today's lecture, you can just think of as higher order polynomials. Higher order polynomials. So as we increase the number of polynomial terms, we can send our training error all the way to 0, right? We can literally send it all the way to 0. But our out of sample error will not be 0. Okay, it'll go down a little bit as our model gets more complex, right? OLS will probably do a little bit better than the constant model in most cases, but there's a point where our model gets too complex and begins overfitting, and our out of sample error starts increasing. Our goal when we're fitting models is to try to identify the sweet spot. Even though the training error is going down in these cases, we need to come up with methods to try to identify the point where we minimize our out of sample error. Now, why can't our out of sample error go to 0? There's random noise. There's always going to be random noise out there, right? We can't perfectly predict that random noise. That's explaining that big gap. There's a bunch of random noise out there. We can't always get things perfect, but we can try to minimize it. Everything to the left of that sweet spot, we would call underfitting. Everything to the right of that sweet spot, we call overfitting. Now, based on this picture, it's very hard to perfectly fit. Every model will slightly underfit, slightly overfit. Our goal is to just do as little as possible of underfitting and overfitting. Okay, now that's our goal. All right, so we're done. Thanks, everybody. Have a good weekend.